Truth table.
Truth table. It's the truth table. So it is the truth table where for each of the possible input combinations, what is the output pattern required, that is mentioned in an unambiguous manner. That means for 000 input combination, if I say the output may be 1, output may be 0, that is then there comes the ambiguity. So that is not possible. I have to in an unambiguous manner specify whether the required output is 0 or 1. Okay, I cannot say the output may be 0, maybe 1. That is not possible. Okay, so for any combinational logic circuit design, my starting point is from the problem description. You should be able to realize the corresponding truth table. And what is the truth table? Now, in the truth table, the output is specified in an unambiguous manner for each of the possible input combinations. Is it clear?
Yes, sir.
Thank you. Now, let me come for the other one, sequential logic circuit. Here, in the case of sequential logic circuit, the output not only depends on the input combination, but also it depends on the past history of events that have occurred in the circuit. I repeat. In the case of sequential logic circuit, the output not only depends on the input combination, but it also depends on the past history of events that have occurred in the circuit. I think this is not very that clear, isn't it? Is it clear?
No, sir.
No, sir.
Sure, it should not be. Now let me take one example that will help you to clear the perception. Let the requirement is to realize on logic circuit, which is basically one sequence detector. What is the purpose of the sequence detector? Say this is X, this is Z. X is the input and Z is the output. And the purpose of the sequence detector is to detect whether in the input sequence 1, 1, 0 is present or not. In case in the sequence I detect or the circuit detects the presence of 1, 1, 0 sequence, it will raise the output Z is equal to 1. Otherwise, if the sequence is not available, it will make Z 0. Is the requirement clear? Or should I repeat?
Repeat once.
In X, I am having so this type of bit sequence is coming. First, I am getting a 0, then 0, then 0, then 1, then 0, then 1, then 0, this way. Now, purpose of this sequence detector is to find out whether in this bit stream of X, I am getting the pattern 1, 1, 0 or not. If I get 1, 1, 0 pattern, the output will be indicated that that output will indicate that the pattern has been detected by raising Z is equal to 1. And if the pattern is not present, the output Z will remain 0.
Sir, is it basically searching for a substring 110?
Yeah, it is basically searching for this 1, 1, 0 pattern in the bit sequence.
Okay, sir.
Okay, but remember, at a time, I am getting only a single bit. Here, I have not given any bus. So X is basically one single bit line. But here, one thing is sure, this is coming at the first instant. Then after, at the next instant, this will come. At the next instant, this will come. At the next instant, this will come, like this. So there must be some signal which will indicate to the sequence detector that a next time instant has come. Is it not? So here everything is when you say that I have a 0 now, and the next time I am getting a 0 again, and next time you are saying that I am getting a 0 again. So how do you specify the next time? How do you specify the next time in the physical world, in practical world? What helps to specify a particular time?
Sir, by using delay in time.
No. Forget about those things. I am talking about the standard practical life, usual human life, human being life.
The clock itself.
Clock. That's the clock. The clock timing gives you the indication that what is the current time instant, and what will be the what are the past time instants. So there must be some signal given to the sequence detector circuit, which is also called the clock signal. And normally the clock signal is a square up type of thing. It may have a duty ratio of 50%, it may not have the duty ratio of 50%. By the what is the duty? What do you mean by the duty ratio? What do you mean by duty ratio? Have you heard of this term?
No, sir.
And at most of the time, the clock signal should be periodic. By periodic, what do you mean?
Repeats after a certain
This rising age, this time period will be same everywhere. So let that be TC, the clock period, TC, or you can say it is T. This is called the on period. This is called the off period. Now, duty ratio is T on by TC or T, whatever you say, is ratio. And most of the time we express the duty ratio in percentage. So that into 100.
So could you repeat the name of the ratio?
Duty ratio. Or koda dekbe, it is also called duty cycle. Duty cycle. Duty ratio or duty cycle? The most common term is a duty ratio. Though the ratio means a fraction, but normally we specify duty ratio in percentage. Okay. So if T on is equal to T off, what will be the duty ratio? 50%. Okay. So the clock signal should be a periodic square wave, but it may not have 50% duty ratio all the time. In some cases, I may have less than 50% duty ratio. In some cases, we may have a clock signal having more than 50% duty ratio. In some cases, we may have exactly 50% duty ratio. It doesn't matter. What matters is at which time instant the rising edges or the falling edges are coming. Okay, fine. So the presence of this clock active edge, let us assume that the clock active edge is the rising edge. The arrival of a new clock active edge or the new clock rising edge indicates to the system that a new time instant has arrived. So if the current rising edge is this, the system knows that it's a newer time instant as compared to this time instant. Similarly, when the available rising edge is this one, the system knows that this particular time instant is the current time instant, whereas the past time instants are this. Hope how the clock is indicating the arrival of a new time instant, that is clear.
Yes.
Fine. Now tell me, when the first zero comes, what you now assume that in place of the sequence detector, you are present there. In place of the sequence detector, as if you as a human being is trying to detect the whether in the input pattern that 110 is coming or not. When this current this first zero is there, what will be your impression?
Zero.
What will be your impression? What is this zero? Is it a part of the sequence?
No, not at all.
It is not a part of it. If the current bit is not a part of the sequence, what should be the output?
0.
Zero.
When the second zero comes at the next time instant, what will be the impression?
Zero.
Now, first you tell me the impression, then you go for the output.
Not a part of the
It is
sequence.
not a part of the,
Zero.
so the output is zero. Next.
Not
Next.
matching zero.
Yeah, it is
Not a
it
part
is
of the
not a part of the sequence, so the output is zero.
Zero.
Then 1.
Maybe.
Then what is that maybe? Remember, you have to be very much optimistic.
Sir, we need to check the next bits.
No.
That
How can you check the next bit? The next time instant has not yet come to you.
Yes,
You can
sir.
deal with only the present time instant and the past. Future is not under your control.
Sir, then it will be 1.
No. Why 1?
Sir, because we are being optimistic.
You are being optimistic, but can you say that you have completed the sequence?
No, sir.
So in that case, also you are very much optimistic. You cannot say that the output is 0. Output is 1. What you can say is
it will be zero, sir.
it will be 0. But what is your inference?
Sir, since we do not know what the next bits are, that is why we need to consider for the time being that it is zero.
No, forget about the output. First,
Sir, as we go forward, we'll check the past.
Yes, sir.
time
We
instant.
will keep track of the past, and by that we can say that if the sequence has been detected or not.
No. When you get this 1, what is your inference? Can it be part of the sequence or not?
Yes.
The sequence which I am interested is 110. So as soon as you get 1, what is your inference?
There is a chance it is a part of the sequence.
There is chance, and what chance? What is your inference? Can it be part of the sequence or not?
Yes.
It can be part. If it is if there is a chance of it being a part of the sequence, which part?
So the first bit.
First bit. So as soon as you get this 1, your inference is this is the first bit of the sequence. Why I am saying you must be optimistic? Because you are inferring that this is the first bit of the sequence. You are not saying this may be the first bit of the sequence. What you are saying is this is the first bit of the sequence. That's why I bring that optimistic term here. But though I am inferring that this is the first bit of the sequence, can the output be 0? Can the output be 1?
No, sir.
No, because the output will be 1 only after all 3 bits are detected. So the output is 0. So when you get the 0, next 0, what is the inference?
Our previous inference was wrong.
0.
Fine. So what is the current inference?
Not a
It's not part of
It is
the
not a part of the
sequence.
sequence. So no part of the sequence has been detected as if this is the inference now. Then once again, 1. What is the inference?
It may be part of the sequence.
No, not maybe. I won't go for any may option.
First bit of the
This
sequence.
is the first bit of the sequence.
First bit of the sequence.
But sequence not complete. Then a 0 comes.
Not a part of sequence.
Not a part of the sequence. Then a 1 comes.
First bit.
First bit, but output 0.
Yes.
Then
Second
another
bit.
1 comes.
Second bit, but not a part of
Second bit, but sequence not
but still
complete.
zero. And
Then
not a
another
part of
one
the
comes.
sequence.
Then another 1 comes.
First bit, but zero.
No. What will be
Second
the
bit, sir.
Second
Yeah.
bit, sir.
Yeah. Because I can say that this is the first bit.
Yes.
This is the first bit and this is the second bit. Isn't it?
Yes.
Yes.
So, but still the sequence is not yet complete. When you come here,
Second bit, sir.
1 second, second bit. When you come here,
Once.
sequence complete. When you come here,
First bit, sir.
First bit.
first bit.
Zero.
When you come here,
Second
Second
bit.
bit,
Zero.
when you come here,
1.
1. Acha.
0, 0, 1 again.
0, 0.
then,
0.
then,
0.
okay. So that's the way outputs are generated. The way you have generated the output and the way you have drawn up the inferences at the arrival of any x value, the same thing must be incorporated by the sequence detector logic circuit. Okay, the sequence detector must follow the same logic pattern. See here, when a 1 comes at this particular place, what is the inference?
First bit of sequence.
First bit of the sequence. But when this one comes, what was the inference?
Second bit of sequence or first bit of new sequence.
The value of x is same. Here it is 1, here also it is 1, here also it is 1. But the inference is different. Why so? Why is it so? Why the inference is different? Though the value of x
Because
is
of
same.
previous history.
Because we
That's the
already
history of
encountered one
previous
in the previous
incidents উপর depend করছে. It's depending on the history of previous incidences that have occurred in the circuit. Similarly, here the x value is 0. What is the inference?
sequence has been detected.
It has been detected, and what is the output?
1.
1. But here, same 0 has come. X is 0 only, nothing else. But what is the inference? This 0 is not part of the sequence, and the output is also 0. So though the input value remains the same, but depending on the past history of the circuit, the response of the sequence detector logic circuit should be different. So what I meant earlier is, in the case of combination logic circuit, the output depends only on the present input combination. Had the sequence been one combination logic circuit, in that case, as the input is same, output should have been also same. But here this is not the case. Here the output depends on not only on the present input, but also on the past history of events that have occurred in the circuit. So that's the beauty of one sequential logic circuit. So in the case of sequential logic circuit, the output not only depends on the present input combination or the input combination, it also depends on the past history of events that have occurred in the circuit. So in this specific case of detecting the sequence 110, what are the possible such histories?
First bit and second bit.
হ্যাঁ বলো আরেকবার বলো
First bit and second bit.
no, not true. When you arrive at this particular one,
Yes, sir.
what is your inference?
First bit of the sequence.
This is the first bit of the sequence. Why? Why so?
The bits match.
Because so far no bit of the sequence was available. Is it not? এখানে কি কোন সিকোয়েন্সে কোনো বিট অ্যাভেলেবল ছিল?
No, sir.
So as soon as one comes with that particular history that no bit of the sequence is available so far, if I get a 1, my inference is this is the first bit of the sequence, but still the output is 0. But if I get a 1 here, what is the inference?
Sir, which one?
Second bit.
This one. This is second bit. Why? Why so?
Because we already encountered the first
Already
bit.
we have encountered the first bit of the sequence. Similarly, if I come here, what is the inference?
Second bit.
Second bit. Why?
We've already encountered one
We
first.
have already encountered the first bit and first 2 bits, and I can consider this last second bit to be the first bit again. Okay. Now, if I get a 0 here, what is the inference?
Third bit.
Third bit.
Sequence is complete. Why so?
We got both the bits.
Because both the bits of the sequence, because the first 2 bits of the sequence are already available. Okay. So this is the type of history that you have encountered in the sequentiation problem. So what are those histories? Now tell me.
Whether
What are those histories? কি কি হিস্ট্রি তোমরা এখানে এনকাউন্টার করলে?
No bits available up to the third bit and up,
আরেকবার বলো no bits
No.
available then
up to the third bit, and after that, in the fourth bit, the first bit is encountered for the first time.
no
And-
when you encounter this one, what is the inference? When you encounter this particular one, what is your inference?
First bit of the sequence.
Why is this first bit?
no previous history.
Because here I encountered that this cannot be part of the sequence. So when I have when the present time instant is this particular time instant corresponding to this, I have got this one. So at the last time instant, whatever inputs till the last time instant, whatever inputs I have obtained, from there I can say that no bit of the sequence is available. Is it not? So that's why this one corresponded to that this is the first bit of the sequence. So what are those histories?
So the inputs in previous time constants.
Inputs in
The previous time constants. Like
no,
just
no. How have you arrived at these outputs? or you how we have drawn the inferences. When you arrive at this 1, why are you saying that this is the first bit of the sequence?
So because it matches
the
with the
previous
first
bit.
bit. Oh,
No, no, no.
So
this
because
is
the
not-
previous bits didn't match.
Yeah, so that's the history. That's the history.
Yes, sir.
My history at this particular past history at this particular time instant is no bit of the sequence is available with me. When I go to the next time instant, what is with which is history I am going to the next time instant? That means here. With which history I am going to the next time instant?
First bit is available.
Sir, only first bit was available.
I have encountered the first bit of the sequence. I have already obtained the first bit of the sequence with me. When you come here, with which history have you gone there?
So the sequence didn't match.
No, no, no.
The first
is
bit.
available.
Yeah, I have already encountered the first bit. When I move to the next time instant, what was the history, past history at that time?
Second bit.
Same.
Yeah, no, already two bits of the sequence are already available.
Okay.
Yeah, in one sense you can say that. When I come to this particular time instant, what is the past history? With which past history I move to this particular time instant?
Sir, I have already encountered the first bit.
First
First
I
bit
have
of
already
sequence.
encountered the first two bits. These are the first two bits. When you move to the next time instant, these are the last first two bits which you have encountered. So the history with which you move to this particular time, I'm talking about the time instant, not the value of x. I'm talking about the time instant. When you move to the next time instant at this particular point of time, what is the past history? I've already encountered the first two bits here. But what is the current time, current x bit? 1. So what is your current inference?
Not a part of the sequence.
No. This one is
Sequence didn't match.
no.
Second bit, sir.
This may be the second bit.
Once again. This is once
Second
again
bit,
the
second
second bit of the sequence. So when you move to the next time instant, what is the history with which you are moving to the next time instant?
Two bits already
First two
encountered.
bits.
Two bits already detected. So when you at the next time when you receive a 0, what is your inference?
Sequence has been detected.
Sequence has been detected. Now when you move to the next time instant, what is the history?
First bit.
No, no. What is the history?
No previous history.
No.
Because we matched.
When you move to the next time
Sequence
instant,
detecting the
the sequence
previous.
has been already detected.
previously.
Sequence has been already detected. With that history, you are moving to the next time instant. Is it not?
Yes.
Yes, sir.
So now you are getting a 1. What will be your current inference? Remember here I am talking about current inference and previous history. So what is the current inference?
First bit detected.
First bit detected.
So which history you are moving to the next time instant?
Sir, the sequence has been already detected once.
No. Which history you are moving to the next time instant?
The
No
first bit.
previous bit detected.
First bit of the sequence has
First
been
bit
First
detected.
bit was detected.
So what will be your current inference?
Second bit detected.
Second bit was detected.
Okay. So which history you are moving to the next time instant?
First two bits have been detected.
First two bits have been detected. So what will be with the arrival of the 0? What will be your current inference?
Sequence matched.
Sequence has been detected, and the resulting output is 1.
Yes.
So now which history you are moving to the next time instant?
Sequence has been matched.
Sequence has been detected. So current inference first B. With which history you are moving to the next time instant?
First bit detected.
First bit detected. Current inference,
Second bit detected.
Second bit.
second bit is currently available. Oh, so with which history you are moving to the next time instant?
First two bits of the
First two
First
bits.
two bits
Second
have
bit
been detected.
detected.
So first two bits have been detected. Oh, okay. Second bit has been detected. Fine. Now, what is the current inference?
Third bit detected.
sequence
Sequence,
matched.
sequence
Sequence
detected.
matched.
Output is one. So now we are moving to the next time instant. Which history?
Sequence matched.
Sequence has been detected. So what is your current inference?
Not a part of
First bit.
sequence.
Not a part of the sequence. Not a part of the sequence. Sorry.
So with which history you are moving, you will be moving to the next time instant.
Not a
Not a
no
part of the
available bits.
sequence.
Bit of the sequence is available.
No available bits.
Okay.
Yes.
So now tell me what are the histories that you have found here? What are the possible histories that you have encountered here?
No bit available so far.
1 minute. Let me note them down. First is no bit of sequence is second.
First bit has been matched.
First bit.
Second bit has sorry. First two bits have been matched. Sequence has been matched.
Sequence detected.
Sequence has been detected. Okay. So these are the four possible histories that are being encountered by this sequence detected logic circuit. Now, এই যে history গুলো বললাম, how have you described them? Using natural language, isn't it?
Words.
In words, in a natural language. But will the digital system understand these things?
No, sir.
What the digital circuit can understand? Which
0
language?
and 1.
Yeah, only the binary language it can understand. So now comes the most important thing. These histories which you have obtained from the problem description must be represented to the digital circuit by binary patterns. So rather, I must be able to encode these history information by some binary codes. So kota code binary code lagbe এখানে? How many binary codes would be required to encode these four history? শুনতে পেলাম না। চারটে। So how many binary bits will be required? How many minimum number of binary bits should be required to?
Two bits.
Okay. So এবার সিআর এর দায়িত্ব হচ্ছে বলা কোন কোডটার জন্য কি কোন হিস্ট্রির জন্য কি কোড দেবে। How are you going to assign the codes, Joydeep? Using 2 bits, how many patterns you will be getting? 4, 0, 0, 0, 1, 1, 0, 1, 1. So you must encode no bit of sequence is available this history information by one of those 4 codes. So which code you are going to use here? Remember, when you are encoding there you can associate any code with any history, but you must note that down properly. Now tell me for this first history information, what is the code you are going to assign? জয়দীপ কি আছো ক্লাসে? ওকে, জয়েন করে চলে গেছো।
হ্যাঁ স্যার
বলছি এই নো বিট অফ সিকোয়েন্স ইজ অ্যাভেলেবল এই হিস্ট্রির জন্য কোন কোডটা অ্যাসাইন করবে? তুমি 0, 0, 0, 1, 1, 0, 1, 1 এই চারটের মধ্যে কোন কোডটাকে অ্যাসাইন করতে চাও?
Sir, 0000.
আবার দুটো বিট দিয়ে 0000 কোত্থেকে পাবে বাবা তুমি?
Sir,
দুটো বাইনারি বিট দিয়ে কটা কম্বিনেশন পাও?
স্যার দুটো দিয়ে চারটে পাবো।
কি কি?
স্যার 000110 আর 11।
হ্যাঁ, এই চারটের মধ্যে কোনটাকে নো বিট অফ সিকোয়েন্স ইজ অ্যাভেলেবল তার সঙ্গে অ্যাসোসিয়েট করতে চাও?
স্যার 00 দিয়ে।
ওকে, তারপরটার জন্য ফার্স্ট বিট অফ সিকোয়েন্স ইজ অ্যাভেলেবল, সেই হিস্ট্রির জন্য কোন কোডটা অ্যাসাইন করতে চাও? ঠিক আছে, অর্ণব বলো।
So 01,
দেন
11.
দেন দেন যেটা মানে হয় না, বাকি একটাই পড়ে যাচ্ছে 10। ওকে, সো দ্যাটস দ্য ওয়ে ইউ হ্যাভ অ্যাসাইন্ড দ্য কোডস টু দ্য history information. Now, these sets of binary encoded history information, they are given a special name in digital circuit design, and that is called state of the circuit, state of the system. কি বললাম? I repeat, this binary encoded history, they are given, this binary encoded history is termed as state of the circuit. আমি আর হিস্ট্রি কথা বলবো না। When we are dealing with a sequential logic circuit, we will deal with state, present state, next state. Presently, what is the history? That corresponding encoded pattern is the present state. What will be the next history? Its corresponding binary encoded pattern will be termed as next state. আমি যখন
স্যার এটা আরেকবার বলুন, প্রিভিয়াস হিস্ট্রি হলো প্রেজেন্ট স্টেট।
এবার ধরো, এই যে আমি যখন এখানে এসেছি, when this is my current time instant, what is the history? With which history I have gone to this particular time instant?
00.
No. Oh, with which history? I'm not terming as code state. I'm terming as
Previous bits available.
no.
We have encountered it once, 10.
No.
স্যার কোন বিটটা স্যার দেখতে পাচ্ছি?
What was this zero?
Sir,
Third bit of the sequence.
This third bit, the sequence has been complete. So with which history you are moving to the next time instant, with which history you have arrived at the current time instant?
Sequence has been detected.
Sequence has been detected. So what is the past history when the present time instant is corresponding to this? Sequence has been detected.
Sequence has been detected.
So what will be the past state or the current state? 10 is the current state. Okay, but here what you have encountered?
First bit.
First bit of the sequence. So when you will move to the next time instant, with which history you will be moving there?
First bit of the sequence has been
First
matched.
bit of the sequence. So what will be the next state?
01.
01. Okay, so now I think it's a bit clear. It may not be completely clear. Remember, this sequential logic design is the only area where little bit of intelligence is highly required. All other combinational logic circuit design and other things, they are almost mechanical. But whatever IQ level or whatever the intelligence and the whatever interesting part in the digital logic circuit design is involved in this sequential logic design. This area is the most interesting one, if you can understand that. So I will repeat, I'll be going through this type of designs later also. So even if you are not able to understand it 100%, don't be worried. So you will learn it. But even if you are able to understand it by 60%, 70%, that's fine for today's class. Fine. So
Sir,
what I mean to,
sir, are these states already predefined, sir? 0001.
No, no. What I'll say is, given any sequential logic design problem, you have to analyze it first. And you have to find out from the problem description, you have to find out what are the possible histories in which the circuit may be present.
No,
That's
sir.
the most critical.
I am asking that you have assigned 0 to the first history. So is that
I have not
predefined, sir?
assigned. I have not assigned. Your seers have assigned.
No, sir.
So if your third seer comes and says, no, sir, I don't agree with those two seers, I will say that 1 1 should be the no bit of the sequence is available. Then 1 0 for the first bit of the sequence is available.
Yes,
Then
sir.
0.
Yes,
So
sir. Yes, sir.
I'll accept that one also.
Okay, sir.
It can be designed in that manner also. Remember here what I have mentioned. These states are nothing but the binary encoded history information. So whenever you are going for any encoding, that encoding may be of any type.
Okay, sir.
When you went for the BCD generation, what I told you, there are how many possible BCD encoding rules? But I think 16 C10. Those many BCD encoding rules are possible. Out of which certain rules we have standardized. That's all. Similarly, here also there will be a lot of possibilities. That possibilities of encoding. So we whatever code you have taken, you follow that one, no problem. But definitely you have to mention which state code you are assigning for which history. That you must have to mention. Without that, your answer is not correct. Okay, fine. So given any sequential logic design problem description, you have to first analyze the problem. Why we'll analyze? We'll analyze to find out what are the possible histories in which the circuit may be available. Once you can identify the possible histories perfectly, almost 40% job is done. That analyzing the problem and from there identifying the possible histories, that completes the 40% of the job. And whatever next things are left, that is almost mechanical. Next, you have to assign state codes to those history. And
Sir,
those state codes must be unique. Origin.
sir, can there be any other history apart from these four?
In that case, your state assignment is not proper. You have to identify all possible histories.
Okay.
All means all. In this specific example, there are only 4 possibilities.
Okay.
Okay. And if you miss out one particular history, definitely your answer is wrong. Okay. So you have to you should be able to identify all possible histories which may be present in the circuit. That identification is very critical. And your intelligence or IQ level is required for that identification only. Fine. After identifying the states, what is the after identifying the histories, what is the next step? Now you have to assign state codes for those history informations. Next, you have to go for one state transition diagram. These things will not be clear today. When I'll go for the explicit design of the sequential logic circuit, that will be clear later on. Now let me give you the block diagram for one general sequential logic circuit. By the way, where normally the histories are stored in practical life?
The memory.
In memory. In memory. In our memory or in book form in some library. So that also I can say that some sort of memory. So same thing is true in detailed circuit also. If you have to keep track of the history information, you must have certain memory element. So keep that mind. Yeah, keep that in your mind. CL stands for the combinational logic. This is the block diagram of a general sequential logic circuit. Should I start explaining this or should I give you some more time?
30 seconds.
Okay, fine, no problem. By the way, one thing I must tell you that I am really very happy with your with this class. Why you know? Because the way you are responding to me is very fine. Normally in offline mode class, I can understand by seeing the faces of the students whether they are understanding what I am talking or not. But in online mode, that is not possible. So here it is the only way. If you can raise your doubts instantaneously, then only I can understand whether you are getting my point or not. So that way, I am really thankful to you all. Thanks.
Sir, it's a block diagram of what?
Sequential logic circuit.
Thank you.
This is a block diagram of one general sequential logic circuit. I'll draw certain analogy with the example that we have seen just a few minutes back. while explaining this block diagram. In that sequential logic circuit example, what is the value of M? With
One
reference,
only, sir.
yeah, only one, because there is only one single input, that is X. So the value of M is equal to 1. What is the value of P?
Also
One.
One.
That's also 1, because there is only a single output. But there may be certain cases where the value of M is more than 1, and where the value of P is also more than 1. Fine. How is the output in that particular example decided? Say I have got X is equal to 1. Whether the output will be I have got X is equal to 0. Now whether the output will be 0 or 1 depends on what?
state information and present
State
information.
information. There is a present state information. Under which present state information, forget about the state information. Now consider the history information. Under which history information the output will be 1? When X is equal to 0?
Detected.
When second bit is detected. When the second bit is detected.
So under that condition, if my current input X is equal to 0, in that case my P should be my output Z should be 1. Otherwise, for other present histories, if X is equal to 0, output will be 0. Okay, fine. So now that history, I have told you that history should be encoded in binary and should be termed as, the history information should be encoded into binary. Yeah, exactly.
State of the system.
The state of the system. When you are currently at particular time instant, it is the present state that identifies what is the past history. When you are at a particular time instant, it is the present state that identifies what is the past history of the circuit. So now tell me, what should be the value of N? Because how many bits should be there in the present state?
2.
2. Because there are 2 bits required to encode those 4 histories. Hope you understand. If
Yes,
anybody is having any doubt, please raise that doubt immediately. Fine. The value of N is 2. Now, for which present state, for X is equal to 0, output will be 1?
Sequence has been detected.
No, which present state? I am not now saying
1 0 1 0.
no, not 1 0.
1 1, sir.
1 1. First 2 bits have been detected. In that case only, if the current input is 0, then I will say that my sequence is now complete.
Yes, sir.
Isn't it? So when this present state pattern is 0 1 1 0. What is that?
1 0.
1 1 1 1.
One.
This is 1 1. So when this is 1 1 and this is 0, in that case my output should be 1. But if it is instead of 1 1, if it is 0 0 0 1 1 0 anything, in that case the output will be 0. Is it not?
Yes, sir.
Yes, sir.
Fine. Fine. Now, say this was 1 1. What will be the output? What will be the output?
1.
1.
1.
Now, what should be the next history? This is what has happened in the current time instant. So when I will move to the next time instant, with which history I will move there?
1
Sequence has been detected.
sequence has been detected. So what should be
1 0.
One
next
zero.
time instant? What should
1
the
0.
so 1 0 should be the next state. But what I am saying is, it is I am not terming this as next state. What I am terming is this next state information. Why I am saying this as next state information, that will be clear to you at a later point of time. But forget about the next state information. Let me term this as the next state itself. Let me term this as the next state instead of next state information. Let me term this as next state for the time being. But later you will say that it should not be termed as next state. It should be termed as something else other than the next state, and that's why this next state information is the more relevant term. But for the time being, you consider it to be next state. So in that case, if this is the next state, then what is the value of q?
1 0.
No, what's the value of q? What is the q? Q is the
2 bits.
pathway. Q is the pathway, isn't it?
So two.
Yes, sir. Yes, sir. 2.
2. 1 then q is 2. So now what will be the constituent 2 bit?
1 0.
So that should be 1 0. Okay. So remember, this next state will be generated by the circuit to be 1 0, but it will not be instantaneously propagating to the output of the memory as 1 0, because it is the clock signal which is indicating the arrival of different time instants. You are presently at this particular time instant. Okay, there your present state is 1 1. X is 1. Sorry, X is 0. Sorry. X is 0. So output you have generated to be 1. So what is the next state that you have generated? What is the next state that you have generated?
1 0.
So if that 1 0 is reflected to the memory output at this very time instant itself, so things will not work properly. The memory should wait for the arrival of the next time tick before propagating its input
can you
to the output.
Sir,
Please
can you
explain
please
this part
repeat?
again.
Repeat 1 second.
What is the purpose of the clock signal? You just tell me. What is the purpose of the clock signal? Clock signal the key indicate korche. The clock signal, it is the clock signal which is indicating the arrival of a new time tick or new time instant. Is it not? The arrival, the clock signal, the purpose of the clock signal is to indicate to the system the arrival of the next time tick or the next time instant, or to distinguish between different time instants. So here, if we are considering the rising edges of the clock signal are indicating to the system the arrival of the different time instants. So if at the current time instant this rising edge is present, so the next time tick will come here after at which time instant? Now when the next rising edge of the clock signal will come. Similarly, after another clock pulse, when the next rising edge comes, I'll say that another new time tick has come. Okay, so as a discrete times are there, time is not continuous here. I am having discrete times. So here I have one time instant. Here I will be having the next time instant. Here I will be having the next time instant. This way it will propagate. Is the clock signal clear?
Sir, can you explain it once more? I couldn't understand.
Which part bolo baba?
স্যার একটু স্টার্টিং থেকে বললে ভালো হতো, ঠিক করে বুঝতে পারি।
স্টার্টিং থেকে মানে কি সিকোয়েন্সিয়াল ব্লক ডায়াগ্রাম থেকে?
হ্যাঁ স্যার।
ওরে বাবা, সেটা তুমি তাহলে কাছে অন্য কারোর কাছে বুঝে নিও। ওই এতখানি এত কাছে একদম শুরু থেকে বলতে হবে।
স্যার না হলে তাহলে আমি ওই ক্লাস রেকর্ডিং করছি ওইটার থেকে দেখে বুঝে নেবো।
ঠিক আছে। Now, what is this clock? As I have explained earlier also, what is the purpose of the clock signal? ঘড়ি দিয়ে তোমরা কি করো?
টাইম ইনস্ট্যান্স মেজার
Time instant দেখো। এখানেও clock signal purpose is the same thing. The arrival of the newer rising ages indicated the arrival of the newer time instant. That's all. Ever somebody may say that I may not, I am not that happy with the rising ages. I should work with the falling age. Fine, no problem. You can work with the falling ages also. So there, the arrival of the newer falling ages will indicate the arrival of the newer time instance or the newer time ticks. Time tick, I'm T-I-C-K, tick. Okay, so when the present time instant is this one, that means in the circuit, this particular rising age is available. And when will the next time tick or the next time instant come?
After what time period?
When the next rising age of the clock signal will arise?
after one time pulse.
Yeah, after one clock period. So that's why I'm saying that here the time is not continuous. The time instants are separated by one clock period each. From one time instant to next time instant, there is a difference of one clock period. So I won't say that the time here is continuous. I won't say that. Okay, so when there is a clock sequential circuit, there the time is not continuous. Here the time instants are separated by clock period, by one clock period. Fine. Now say when the present time instant is this, that means when the present clock rising age corresponds to this, my present state was 1, 1. My aim was, my x was 0. So what was the output?
1.
So now what should be the state when the next time instant will come?
1 0.
1 0. But somebody has to prepare that. As soon as your output, you are working with this particular time instant, there itself you should prepare what should be the history for the next time instant. Remember, what you are doing today, that should be the history for you tomorrow. So how will you know when you move to tomorrow, how will you know what is your history? Either you should memorize what you have done in your memory, or you should write down what you have done in a diary. Then only when tomorrow comes, you will identify what was the history that you have created today, that you are creating today. So whatever you are creating today for as a history for tomorrow, that you must write somewhere, either in your memory or in your diary. You got my point?
Yes, sir.
So same is true in the case of sequential digital circuit also. So at the current time instant, that means at this particular time instant, whatever you are doing in the circuit, what you are doing? Now, what you are doing is, we know here that the past history is saying that first 2 bits of the sequence is available. Where from you are identifying that? Now from this present state. And you know that the present input is 0. Where from you are knowing that? The from present x value. So from these two considerations, you know that my current output should be 1. And when why the output is 1? No, because the sequence has been already completed. The sequence has been detected. So when I move to the next time instant, that is somewhere here, what should be my history? The sequence has been completed. So who is generating that next state information or the next state? For the next history, what should be the next history? Somebody must be preparing that. Who is preparing that?
Next step.
This is the next state combinational logic. It is the headache of this next state combinational logic circuit to generate the next state, or truly speaking, it should be generating the next state information, which should get translated as the present state at next time instant. But remember, it is being generated in the current present state only. That means when you are here at that time instant, you are generating this. Now, if you transfer this instantaneously here, what will happen? This present state and the next state, they will overlap.
হ্যাঁ ওই টাইম ইনস্ট্যান্টের জন্য কারণ
So,
মেমোরির মধ্যে
it
ক্লকের
is
সব
as if it is not waiting for the next time instant. So in this time instance only, it will identify that, okay, my present state is 1 0. That means the sequence has been already detected. Now as the input is still 0, so output is 0. So output of 1 hoy সঙ্গে সঙ্গে 0 হয়ে যায়. So that's not the required thing. What I require is, though the next state has been generated, or the next state information has been generated by the next state combination logic at this particular time instant, it should not propagate to the present state at that same time instant. It should get memorized somewhere. Where? At the input of the memory. But the input of the memory will not be propagated to the memory output till the next time tick, or till the next rising age of the clock comes. So that means this 1 0 will reside at the memory input. And when the next rising age comes, that 1 0 will move to the output of the memory. So now the present state becomes, now the present state becomes
1 0.
1 0. Now it is 1 0. Now say the present input is 1. So what will happen to output?
0.
0. So output is 0. What should be the next state?
First bit encountered.
0 1.
First bit encountered. So what is the next state?
0 1.
0 1.
0 1. It is 0 1. Will it move to the memory output instantaneously?
No,
No, sir.
So it will reside here. When the next time tick comes here, that is the next rising age comes, this will be translated here. So the present state is no longer 1 0, it is now 0 1. Now another one comes. So what will be the output?
0
0. So what's the next state?
1 1.
1 1. So once again that will come and stay here. It will wait for the next time tick. So when this next time tick comes, that will be reflected here. This is 1 1. It is once again 1. What will be the output?
1
0.
0.
0
0.
0.
What is the next state?
1 1.
1 1. So once again 1 1 will remain here. It will wait for the next time tick. When the next time tick comes, once again that 1 1 will copy to the output. So output will remain as 1 1. So this way the things propagate.
Sir,
Well,
sir, how the next state combination logic will create the next instant?
It is not creating the next instant, it is the creating next state.
Yes, sir. Means how it will create the binary code.
But for that, that combination logic has to be designed. Accordingly, the combination logic has to be designed. How that combination logic will be designed, so that we'll learn later.
Okay, sir.
But one thing is pretty clear here in this block. How in this block diagram, how many blocks are there? How many distinct blocks are there?
3.
3, out of which 2 are basically combination logic blocks. This output combination logic block, and the second one is the next state combination logic block. By the way, you keep it in your mind, though here I have explained it by the thing that the next state combination logic is generating next state, but truly speaking, that should be next state information. What is the difference between the next state information and the next state? That we shall learn later. What is the difference between next state information and the next state? That we shall learn later. But for the timing, for this specific example, we have considered the next state information and the next state both are same, but that will not be true always. There is only a specific case where the next state information and the next state will be same, but there are other cases where the next state information and the next state, they are basically different. Why they are different, why they may be same, that you will all learn later. But one thing is pretty clear that in this block diagram, I have 3 distinct blocks, out of which 2 are combination logic blocks, and the third one is
Memory block.
Memory block.
so unless we learn how to design combination logic circuit, can we proceed to the design of a sequential logic circuit?
No, sir.
No, sir.
So that means henceforth we shall concentrate only on the combination logic circuit design. So after finishing that, only we'll go for the sequential logic design problems. Okay, fine. There I have another point here. There are 2 types of sequential logic circuits. Sequential logic circuits are also called sequential machines. There are 2 types of sequential machines. Moore machine and Mealy machine. What is the difference between this Moore machine and Mealy machine? By the way, what is the difference between combination logic and sequential logic?
One depend on the current input and other depend on the.
Be more specific. Combination logic টার্মের মধ্যে কিন্তু ওই স্পেসিফিক টার্মটা ইনক্লুডেড রয়েছে. In the case of combination logic circuits, the output depends only on the present input combination. From that term input combination, I get to the circuit type combination logic circuit. So while defining the combination logic circuit, you must be specific about mentioning the present input combination. So output depends only on the present input combination. Now, what for the sequential logic circuit?
It also depends upon the history.
The past history.
Yeah. So the output not only depends on the present input combination or the input combination, but it also depends on the past history that have occurred in the circuit. Now, what is the difference between the Moore machine and Mealy machine? In the case of Moore machine, the output depends only on the past history of the circuit, not on the present input combination. In the case of, I repeat, in the case of Moore machine, the output does not depend on the present input combination. It only depends on the past history of the circuit. I again repeat, in the case of Moore machine, the output does not depend on the present input combination. present input combination উপর depend করে না. It only depends on the past history of the circuit. What is the case of Mealy machine? The output depends on both the present input combination as well as the past history of the circuit. So here, this block diagram corresponds to what type of machine? What type of
Mealy machine.
machine? Had it been Moore machine, what difference will be there?
Sir, present state won't be there.
In the output combination logic, I won't have this. Other parts will remain same as it is. Is it clear? The output will not depend on the present input combination. It will only depend on the past history of the circuit. And how do you get the past history of the circuit? From the present state. So in the case of output combination logic, only the present state will be the input. But in that case, now can you say how the input is affecting the output? Will you say that the input is irrelevant here?
No, sir.
No, sir.
How the input is relevant?
Sir, it helps us to find the next step.
Yeah. It is the input which controls what should be the next state. And at the next time instant, this next state gets reflected as the present state, and that present state affects the output. So as if the present input is not being able to control the present output, but it may control future outputs. You got my point?
Yes.
The present input is not directly controlling the present output, but it is controlling the what next state you are generating presently. And the next time instant, that present state will get reflected as the present state. At the next time instant, the next state will get reflected as the present state. And through that present state, the input is indirectly controlling the output. Okay, the input is not directly controlling the output, but through the state information, it is indirectly controlling the output, but that definitely is not instantaneously. It is affecting the output at a later point of time. So that's what happens in the Moore machine. But if it is Mealy machine, definitely the input will go to the present input combination, will also affect the output. So that's the only difference between Moore machine and Mealy machine. So these questions are often asked. Difference between combination logic circuit, sequential logic circuit, difference between the Moore machine and Mealy machine. I hope these points are to some extent clear.
Yes.
Fine. Now let us.
No, sir.
Bolo.
Sir, from suppose from memory, when the memory output we are generating a present state, and that present state is being circulated, and we are getting some memory input after from the next state information. Is that process instantaneous?
No. Yeah. Remember the combination logic circuit. That basically, as soon as you give some input combination, the output is instantaneously generated.
Yes.
But instantaneously means ignoring the propagation delay. Ignoring the propagation delay of the constituent logic gates, I can say that the output is almost instantaneously generated. Definitely, ideally, that is the situation, but practically there will be certain delay, but that delay is of the order of nanoseconds.
Yes.
Okay, because the propagation delays are of the order of few nanoseconds. So, fine, thank you. Now let me move to the combination logic design problem. I have mentioned one thing while discussing about the combination logic circuits. What should the starting point of the combination logic design? I have referred to that particular term today itself. What is the starting point? Given the problem description, what is the first thing that, yeah. Given the problem description, you have to first arrive at the corresponding truth table. It is the truth table where for each possible input combination, what are the required outputs that are listed in an unambiguous manner. Say my truth table for one particular logic design problem, say there are 3 inputs A, B, C, only a single output F, and the truth table will be having how many inputs and how many outputs? How many input variables and how many output variables should be there in the truth table?
8 input variables.
3 inputs, 1 output.
So how many columns will be there in the truth table? Now 4. 3 corresponding to the 3 inputs and 1 corresponding to the 1 output. So these are 4 columns that should be there in the truth table. How many rows should be there?
8. 8.
Fine. Let us arbitrarily decide that from the problem description, the truth table that we have arrived at is something like this. Some arbitrarily I have assigned it. I do not know what this truth table corresponds to. That I do not know. But from some problem description, let us assume that this is the corresponding truth table. Is it clear?
Yes, sir.
Fine. Now, from as my starting point is the truth table, obtaining the truth table from the problem description, that starting point is now ready. Now I have to go for the actual design. Now there are 2 types of design aspects. In the first design aspect, let us find out the input combinations for which the required output is 1. I repeat, let us find out the input combinations for which the required output is 1. How many such input combinations are there in this example?
3.
3. One is here, second one is here, and the third one is here. Now, for each of these input combinations, forget about each of them. Let us take the first input combination for which the output is 1, 0, 0, 1. Now, generate a product term in such a manner that for 0, 0, 1 input combination, the product term will produce a logic 1 output. I repeat, what is my requirement? Your requirement is now to generate a product term. Product term means logical product term, that is the logical AND operated term. You have to generate one product term in such a manner, the product term involving the variables A, B, C, in such a manner that for A is equal to 0, B is equal to 0, and C is equal to 1, the product term will produce a logic 1 output. And what should be that product term?
A bar, B bars.
A bar, B bar, C. If my product term means what? The three input variables A, B, C should be ANDed. But they should be ANDed in such a manner that that AND operation should produce a logic 1 output when A is equal to 0, B is equal to 0, and C is equal to 1. Now the AND operation will provide a logic 1 output when all three constituents are 1. So when A is equal to 0, the contribution of A in the product term should be 1. So how that A should be reflected in the product term? As 1 A bar. Because for A is equal to 0, my contribution to the product term should be 1. Individual AND gated, a tinte input should be 1. Then only the output will be 1. So when A is equal to 0, how can you produce a logic 1 here?
A bar.
By connecting here A bar. When B is equal to 0, how can you contribute by 1 here? By connecting B bar here. When C is equal to 1, how can you contribute 1 here by connecting
C.
So that means this AND gate is nothing but this A bar B bar C. So that's the product term. That's the product term where which produces a logic 1 output for, for the input combination 0, 0, 1. I think it is clear, more or less. What about the next product term?
A bar B C bar.
And the final one?
A B C bar.
Now, what is your actual requirement from the truth table? Should the output be 1 only when A is equal to 0, B is equal to 0, C is equal to 1? Achha, by the way, the one thing I missed. Now this product term A bar B bar C, for which input combination this produces a logic 1 output? The product term A bar B bar C, for which input combination this produces a logic 1 output?
0 0 1.
0 0 1.
For truly speaking, involving A, B, C, how many possible combinations are there?
8.
8. Out of which 1 I have mentioned here. So how many are left? 7. For all the 7 input combinations, what will be the contribution available from this A bar B bar C? For all other 7 input combinations, what will be the contribution? That means what I mean to say is, what will be the output available from this product term A bar B bar C?
0.
0 only.
0.
Okay, so that means this A bar B bar C term, this produces a logic 1 output for the 0 0 1 input combination, and for all other input combinations that produces a logic 0 output. Similarly, A bar B C bar, what it does?
0 1 0.
For 0 1 0, it produces a logic 1 output, and for all other 7 input combinations, it produces logic 0 output. What about A B C bar? It produces a logic 1 output for
110.
What for 110 input combination, and 0 for all other 7 input combinations. Now, what is your actual requirement as depicted in this truth table? The truth table says that my output should be 1 if the input combination is 0 0 1 or 0 1 0 or 1 1 0. So if input combination is 0 0 1, you are getting logic 1 output from which circuit, for which term?
A bar B bar C.
And from this and this, what you are getting?
0.
0. Now, if 0, 1, 0 is the input combination, what will happen? I'll be getting logic 1 from A bar B C bar.
Yes, sir.
But from A bar B bar C or from A B C bar, I'll be getting 0.
Yes, sir.
Whereas if the input combination is 1, 1, 0, what will be getting?
A, B, C bar is
Yeah,
1.
that will give you logic 1 and the other two will give logic 0. Now, if the input combination is 1, 0, 0, what will happen?
1, 0,
0
0.
0 from all.
0 from
So,
all 3.
what should be your function, ultimate function? This should be the logical
Plus,
sum
plus.
of these three.
Yes.
That should be the logical sum of all these three terms, or of all these three product terms. So if the 0, 0, 1 input combination is there, I'll be getting 1 from here, 0 from here, 0 from here. If it is 0, 1, 0, I'll be getting 1 from here, 0 here, 0 here. If it is 1, 1, 0, in that case, I'll be getting 1 from A bar, A, B, C bar term. But this logical sum that will produce f is equal to 1 in all these three cases. And if I go for any other 5 input combinations, all three will give you logic 0 value. So the output will also be logic 0. Is it clear?
Yes, sir.
So here what you have done, you have taken this F is nothing but a logical sum. This is a logical sum. Logical sum of what? Several product terms. These are the product terms. These three are nothing but the product terms. So how the function has been realized here? The function has been realized here as a summation of several product terms. So this type of combination logic relation is called sum of products type of CL combination logic relation, or সংক্ষেপে যেটাকে আমরা বলি SOP, sum of product form. The function E has been realized here in the SOP form or the sum of products form. Summation, logical sum means logical sum, product means logical product. So this is nothing but one summation, logical summation of several logical product terms. So that's why this is called the sum of product type of realization or SOP type of realization. So what are the gates that are required here? What are the logic gates that are required here? Forget about the inverters. You assume that the literals or the variables are available in both complemented as well as uncomplemented form.
And get and or get.
And get and or get. How? Now, if I ask you to tell me what is the circuit complexity, how do you specify that? First thing you have started it that the circuit consists of AND gate and OR gate. I am forgetting about the inverters. I am assuming that variables are available in both complemented as well as uncomplemented form. If they are not available, then in that case, all inverters should also be constituting the part of the circuit. Now, here, how many AND gates are required?
2.
3.
3 AND gates.
6.
About 6 কে আসছে?
3, sir.
There are 3 AND gates required. One for realizing A bar B bar C, one for A bar B C bar, the third one is for A B C bar. And all these 3 AND gates are having how many inputs?
3 each.
3 input each.
So if I have to specify the circuit complex, আমি এই মাঝখানে জায়গাটা মুছে দিয়েছি। If I have to specify the circuit complexity, I should say that it involves three number of 3 input and And what else?
One or get. One or get.
Number.
3 input, 1 OR gate.
That's the circuit complexity. Okay. আচ্ছা আমাকে এই এক্সপ্রেশনটা একটু একজন কেউ বলে দাও। f is equal to কি? a
bar b bar c plus a bar b c bar plus a b c bar.
Thank you. Achha, now if I draw the circuit diagram for this circuit, first I'll be having 3 AND gates. Here I have a bar, b bar, c, then a bar, and then I'll be having 1 OR gate. This is the circuit. Hope this is clear to you.
Yes.
Yes, sir. Now, in this in Boolean algebra, we know that my f is equal to f bar.
Sir.
Follow.
Sir, why are not we considering the inverter?
I mentioned now, but we are basically assuming the variables and their complement are already available.
Okay, sir.
If that is not available, definitely we have to consider the inverters also. Okay. Here, just to conserve space, we are considering the variables are available in both complemented as well as uncomplemented form. Otherwise, I have to draw those inverters again. That's all.
Okay, sir.
Right. Achha, by the way, this expression is in which form? Just some few minutes back, I have explained.
SOP.
SOP, sum of products. Now, here, how many stages are there in the circuit? 2. In the first stage of what type of components are there?
And
in the second stage, what type of component is there? So, SOP is equivalent to and or type of realization. SOP relation is also sometimes referred to as and or type of realization. Fine. Now let me come back. I know that my f is equal to f bar bar. So definitely I can try this one. I can try this one.
Yes.
Apply De Morgan's theorem.
Yeah. Now apply De Morgan's theorem over the lower bar. So that will become. So this f will now become a bar b bar c bar dot a bar b c bar bar dot a b c bar and then full over bar. Is it not?
Yes.
Now to realize this circuit, this conventional logic in this particular format, what are the circuit components that are required? What are the types of logic gates that are required?
Only and.
Only?
And.
No. Only NAND.
The NAND gate.
Only NAND gates are required. So, what if I ask you what is the circuit complexity? What will you say?
3 numbered.
It has been reduced.
No, it has not been reduced.
4 NAND gates.
4 NAND gates. Then you must have to specify the number of inputs also.
3 inputs.
All
Three
three
input
inputs.
each.
All
Three
three
input
inputs.
Four
each.
number of 3 input NAND gates. And if I go for the circuit complexity was both are same. Previous version and this version both are same. They are also by circuit complexity. What I mean is number of gates multiplied by the corresponding input values. So earlier that was 3 into 3 plus 1 into 3. So that means 9 plus 3, that means 12. Here it is 4 into 3, that is 12. So complexity was both the same. Okay. So if I now try to draw this circuit, what the circuit corresponding circuit will look like? In the first stage, what you will be having?
Three NAND gate.
Second stage is also 1 3 input NAND gate. So once again, this is also a two-stage circuit. But in the first stage, what type of components you are using?
And dot.
No, NAND. In the first stage.
Sorry. Yes, sir.
So this is once again equivalent to NAND. And what is the second stage?
NAND.
So this is the NAND version. Or the circuit involves only NAND gates. Now, one peculiar thing you will find out, this these two configurations, their wirings and input outputs remain the exactly same. Only thing is, in the first stage, wherever I had AND gates, those AND gates are getting replaced by equivalent input NAND gates, and the second stage OR gate is getting replaced by one equivalent input NAND gate. Otherwise, see, the wiring and the input, presence of the inputs and the outputs, everything remains the same. Only thing is, this fellow is now being replaced by one equivalent input NAND gate. This is also being replaced by one equivalent input NAND gate. You will come back to this. You will come to this one. So the circuit configuration connection-wise, that remains same, but the constituent elements are getting changed. In the AND OR version, wherever I had the AND gates, I am replacing in the NAND version, I am replacing them by equivalent input NAND gates. And whatever OR gate I was having in the AND OR version, I am replacing that by once again one equivalent input NAND gate. Thereby, I can establish that one AND or SOP is equivalent to one, can be realized in AND OR format, that can also be realized using NAND format. Now, this relation proves that NAND is one universal logic gate, because any combinational logic can be realized in the SOP format, and any SOP relation can be realized using only NAND gates. This is the proof. This is the proof. This is the proof. So that also proves that using NAND gate, I can realize any type of logic circuit. So that's why this NAND is called one universal logic gate. So you can prove that NAND is one universal logic gate in two ways. In one way, you can prove that this using NAND, you can realize all other four basic logic gates. And the second thing is, second way in which you can prove is that you can establish that using only NAND gates, you can realize one combination logic circuit in SOP format.
স্যার বলছি আমাদের ক্লাস আছে এখন শেষ করিয়ে দেবেন
These two ways you can prove that NAND is one universal logic gate. হ্যাঁ, কেউ কিছু বলছিলেন?
Sir, we have class from 12
বলছি
itself.
ক্লাস আছে 12টা থেকে
হ্যাঁ হ্যাঁ, কি হলো ক্লাস? সবে তো 1 মিনিট হয়েছে।
Sir, এখনই ক্লাস আছে স্যার।
সো হ্যাঁ, সে তো 5 মিনিট পরে শুরু হলে কোনো ক্ষতি কিছু হয় না। আমারটা তো 5 মিনিট পরে শুরু হয়। হ্যাঁ, anyway, so this NAND, using only NAND gate, you can realize any conventional logic circuit, and that proves that NAND is one type of universal logic gate. So in the next class, that means on Tuesday, we'll start for the second version of conventional logic circuit design. That will start in the next class. Now,
Sir, is this true for all cases? Like if there is any kind of logic circuit using AND or AND and OR gates, if you replace all of them by NAND gates, will it be the equivalent circuit?
No. If it is in SOP format, then only.
Oh, okay. In SOP format, if it is there, so then it will be equivalent.
In SOP format, definitely that SOP can be realized using only NAND.
So we'll just replace all the AND and OR gates by NAND gates, and we'll get the same exact function.
Yeah.
Okay, sir. Okay.
But definitely that should be in two-stage version. The first stage there should be only AND gates. The second stage there should be only single OR gate. Then only you can realize it.
Okay, sir. Okay, sir.
Okay. Now do one thing, as there is not much time. You just in a chat box you give your attendance and leave.